So, welcome back, everyone. Let's continue with our real analysis class. This is lecture number 5. I hope you're having fun until now. Real analysis 2020. Okay. This is lecture 5. And I want to finish today the construction of the Lebesgue measure. Okay, so this is the goal for the class today. The Lebesgue measure, part 2. Okay, so I hope you guys are having fun. You have a new set of exercises to think about that I sent you last Thursday. I hope you're finding it a little bit more enjoyable. And if you keep doing that, if you keep finding it enjoyable, it's going to be better and better every week, okay? So let's remember where we are in this class, right? So the first 3 lectures, we discussed the basic concepts of measure theory, generically speaking. We discussed sigma algebras, we discussed measurable functions, and measures and integration. First, we started integrating simple functions, and then non-negative functions, and then general L1 integrable functions, right? We discussed the main theorems of convergence, monotone convergence, dominated convergence, and Fatou's lemma. These are going to be pillars, cornerstones for the rest of this course. So we're going to be using this all the time. And then we moved, in the last class, to something slightly more concrete. We wanted to define properly the Lebesgue measure on RD, on the Euclidean space RD. This is a measure that is going to be also, the main measure for the applications that we have in mind, because real analysis is going essentially to talk about functions, inequalities, and their properties in the Euclidean space. But you may need abstract measure theory depending on what you decide to do in the future. I mean, you may need it for probability, you may need it for dynamical systems, and so on. So it's good to have a generic background and also to know how to use it in the specific case of RD. So the goal was to define a measure which somehow extended the notion that we have for measures of the forms that we understand. For example, cubes or rectangles or circles, We decided to go with cubes, okay? So we saw some propositions in the beginning of last class, and we decided, this is just a review. We defined what we call the exterior measure. Okay? And this exterior measure we call M star of a set E was just the infimum over the sums of the volumes of cubes, Qj. My cubes here, if I don't say anything, they're always meant to be closed cubes. Okay? Where the infimum is taken over the collections Qj cubes, and E contain the union of Qj. It's a countable union. So you can take all coverings of E by countable unions of cubes, then you sum up their volumes, and you take the infimum of this of all possible coverings that you can imagine. The good thing about this definition, the nice thing, is that this is well defined for all subsets of RD. You can give me any subset, and this is a well-defined number, okay? It might not be meaningful for what we're going to do in the future, but it's there if you want to use it. That's the exterior measure of the set. The name is very suggestive. It's exterior because you're kind of covering from the outside. You're taking the infimum of the volumes of these things, right? So we expect that if a set is somewhat well-behaved, doesn't have too many fractal things and crazy things going on, you should be able to approximate it reasonably well from the outside, okay? So we proved the following things. So let's just review what we proved, because this is going to be somehow useful. So let me write down, and we have it written here, what we proved. So basic properties of the exterior measure, we called it monotonicity, in the sense that if a set E1 is contained in E2, then the exterior measure of E1 is less than or equal than the exterior measure of E2. What else did we prove? We proved this countable sub-additivity. The sense that if a set E is the union of sets Ej, j from 1 to infinity, then the outer measure, the exterior measure of E was less than or equal than the sum of the exterior measure of these Ej's. 3, we proved that for any set, the outer measure of the exterior measure of E is equal to the infimum of the exterior measure of open sets for open sets that contain E. This is important too. 4, what else? Oh, this was good. If you have a set E, which is the disjoint union of two sets that are apart such that their distance is bigger than 0, then the exterior measure adds up. And 5, we proved that if a set E is the union, almost disjoint, it's the almost disjoint union of cubes, and remember what we mean by almost disjoint. Our cubes are closed, so we say that the union is almost disjoint, and if they are allowed just to intersect in the boundaries, okay? So their interiors are disjoint. So if we have a set which is the almost disjoint union of cubes, then the outer measure, the exterior measure, adds up. Okay. All right, so let's keep this property in mind. Let's keep these 5 properties in mind. And let me just make to you an observation. Brief remark. We proved also in the last class, maybe before to prove these basic properties of the exterior measure, that if I gave you any open set O, I could write O as an almost disjoint union of closed cubes. So every open set you can cover from inside using cubes. And remember that we did this by just taking my grid dyadically. You know, I take the dyadic grid, I take the plane, and I divide in, let's say, the integer lattice. I put the cubes that are inside, and I choose these. And then I further subdivide, you know, every interval in halves. And I take the, you know, the next generation, and then I pick the cubes that are inside. And I keep doing this, and at every step, I pick the dyadic cubes that are totally inside. And I can get a covering of these guys, you know? Okay, so you kind of picked this one and this one in the first generation, and then you move on to the second generation, keep splitting, and you pick the smaller ones, and then you go on and you keep splitting, and you get the next one, and so on. Now, this is just one possible way of covering your open set with cubes from the inside. There could be a million of other ways, but it could be also clever to do it. How would you guarantee that the sum of the volumes of the cubes of your partition, my partition, your partition are the same? Are they the same? Can you do better than me? And the answer is no. In principle, this is not a trivial question. But the answer is no. Doesn't matter how you cover your open set with almost disjoint cubes, the sum of their volumes is the same. And the answer is right here, this property. If a set E, let's say your open set is the almost disjoint union of cubes, then the sums of the volumes of these cubes is always equal to this number, the exterior measure of E, whatever this number is. So it doesn't matter how you cover by cubes, but the sums of the volumes of the cubes will always be equal to this number. So this is a proof that the sums of the volumes of the cubes is independent of the covering. You know. Okay. Keep that in mind. And then we moved on to define what were the Lebesgue measurable sets. Okay. The definition is a set E and in RD is called Lebesgue measurable okay, or simply measurable for our purposes here if for any epsilon bigger than 0 you can find an open set O that contains your set E such that the outer measure, the exterior measure of O minus E is less than or equal than epsilon. Okay, so this is the definition. The set is called measurable. So remember, our goal is to measure the sets. And the nice insight of this theory is that we don't have to measure all the sets. We would like to measure the sets, as many sets as possible, but we don't have to measure all the sets. In fact, given the axioms that we would like for our measure, we shall see maybe in the end of this class that we cannot measure all the sets, you know, because we want our measure to have certain invariances. For example, if I take a set here and I translate one unit to the left, I want the translated set to have the same measure. So I want my measure to be invariant under translations, invariant under rotations, invariant under certain dilations, you know. And this is not going, we cannot measure all the sets given these boundary conditions. Now, and the idea is to define which sets we can measure, and these are going to be called the Lebesgue measurable sets. So the definition is right here. So let's work with this and try to develop properties that will follow from this definition so we can, once we prove these properties, we'll be able to use it in the future, right? So a set is going to be measurable if for every epsilon you can find an open set that contains your set E such that the exterior measure of the difference is small. It's less than or equal than epsilon. Okay? All right. Given this definition, I want to prove to you the following basic properties of the Lebesgue measure. Let's see. All right, so let me see if I need this right now. No. Okay. Maybe I should also define here what is the. So if a set E is measurable in the sense above, we define its Lebesgue measure M, or simply measure. So if a set is measurable, we are going to define the Lebesgue measure of the set simply by taking the exterior measure. So the measure of E will be, by definition, the exterior measure of E. So our goal for the next half an hour is to prove that the collection of measurable sets is a sigma algebra and that M defined as M star in this collection of subsets is a measure. Okay? This is what we are going to do. So let's do it. proposition 2 of today. So these I will call basic properties of measurable sets. First one, every open set is measurable. Second one, if a set has exterior measure 0, then this set is measurable. Number 3, countable unions of measurable sets is also measurable. 4, closed sets are measurable. And 5, complements. Complement of a measurable set is measurable. You see, I find this to be a beautiful symphony of steps, in the sense that we started with very basic facts, and I will keep my motto throughout these classes, you know. A difficult thing will just be a bunch of basic things put together in the right order. So it's kind of right to prove things, as we are proving, in a certain order. It will facilitate our life, you know. You wanted to prove that this is a sigma algebra. Well, you could try, let's prove that it's closed under complements. You see, purposely, I put here, this is the 5th step out of 5, you know. This is not going to be so trivial to prove if you try to start proving this thing first, you know. So the order here kind of suggests the line of reasoning that we have to go. We start with the most basic one. For example, prove. So now we're going to prove this. The first statement is obvious. Every open set is measurable. Well, if your set E is open, for every epsilon, you can choose this O to be E himself. And so O minus E will be just an empty set, and the outer measure of the empty set is 0 by definition. Okay? So 1 is just clear from the definition. So the way that we defined, it's good for some things and not so good for other things. I put in your notes a little bit of an outline of how to construct the Lebesgue measure using the Karateodori theorem. You know, which is a different construction. It leads to the same result. But that construction, for example, it has the advantage of, from the definition, you can find that it's closed under complements, which is not the case here. Here we can find from the definition some other good things easily, and some other things we have to sweat our shirts a little bit to prove. Okay, so number 1, every open set is measurable. That's great. Number 2, well, if a set has outer measure 0, then it is measurable. Let's see, number 2. Let me now move to the other, move to this side. Proof of number 2. Now, if, suppose you have a set that has exterior measure 0. We are going to use this property here, number 3, of the previous proposition. Okay? So by proposition 1, part 3, proposition 1 of the class today, given epsilon, there exists an open set O that contains E, such that, you know, outer measure, the exterior measure of O is just less than epsilon, right? Because this is the infimum of the outer measure, the exterior measures of open sets. So if this is 0, It means that given epsilon, I can choose an open set that I get that this is less than epsilon. Right? But you just notice that, well, O minus E is just contained in O. And by the monotonicity, so I'm using now this one, so I'm going to use 3 and 1. I find that this is less than the exterior measure of O, which is less than epsilon. And then I'm done. For any epsilon, I found an open set O such that the difference is less than or equal than epsilon. Okay? So these are the basic, the first two are very simple. Now, a little bit of a remark. What this property 2, this property, before we move on, what is the significance of this property number 2 that we just proved? A set that has exterior measure 0 will be automatically measurable. The significance of this property 2 is that the measure that we are going to construct is going to be complete, exactly. The Lebesgue measure, once we actually prove what we want to prove, we will be proving that this is a complete measure. Okay? Because if you have a set such that M of E is 0, right? And then if you have a set E1 that is contained in a set of measures 0, then this implies that since E1 is contained in E, M star of E1 is less than or equal by the monotonicity of M star of E, which is just M of E, which is 0. So M star of 1 is 0. This means that E1 is measurable. And also then the M of E1 is actually going to be 0 as well. But this is the conclusion, that any subset of a set of measure 0 is also measurable. So this is the significance of the Lebesgue measure, of this property number 2. All right, I don't want to, maybe I will run out of boards because I don't want to erase this. Let me move here now. Let's try to prove number 3 now, property number 3. Countable unions of measurable sets is measurable. Who? Okay, so let E be a countable union of these guys. Countable unions of EJs where every EJ is measurable. Well, let's try to follow the reasonable steps. So if E is a union of EJ and every EJ is measurable, then given epsilon bigger than 0, we can find there exists an open set OJ that contains EJ such that the outer measure, the exterior measure of OJ minus EJ is less than epsilon. Let's see if we need to adjust here. Maybe put epsilon over 2 to the j. Yeah, maybe we should do this. Okay? Because then, so these are all open sets, right? And then you can just consider O to be the union of all the OJs, j from 1 to infinity. This is obviously an open set. This O, since each EJ is contained in OJ, E is contained in O, so this O contains E. This is good. And O minus E, what's O minus E? O minus E is what? I claim to you that this is contained in OJ. Let's see, it's contained in the union of OJ minus EJ. Is that true? Well, let's see. If a point X is in O and it's not in E, remember E is the union of EJ. So this guy is in O. It must belong to some OJ, because O is the union of OJ. So pick a point X here. It belongs to some OJ, and it does not belong to any of the EJs. In particular, it doesn't belong to the EJ, which is from that particular J that it belonged to OJ. So if a point X belongs to here, it certainly belongs to this side. This set is contained this other one. And then from the monotonicity of the exterior measure, you just get that the exterior measure of O minus E loses to the sum of the exterior measure of OJ minus EJ. And here it was crucial to get epsilon over 2 to the j, because then you can add up. So this is less than epsilon if you add up on j. So you see that we are using this trick of, we are using heavily the countability of the set to make these tricks of getting epsilon over 2 to the j, and we sum over j and get a constant, okay? We could never do this if my union was not countable. All right, so this is property number 3. Countable unions. So this is the first step to prove that this is a sigma algebra, right? So I have countable unions of measurable sets are measurable. So this is good. Now I just have to prove that complements are this whole collection is closed under complements. But let's see. Let's take a look. I mean, there is this item number 4 here. Maybe it's not by coincidence that we should perhaps try to prove this before. So let's now try to prove that closed sets, which is just the first step towards proving that complements are there, because we proved that open sets are measurable. So let's prove that the complements of open sets, which are the closed sets, are measurable. How would we do that? Number 4. Let's see. All right, so let F be closed. Let F be a closed set. Assume for a moment, let's assume first that our F is a bounded set, okay? Bounded in the sense that it doesn't have the exterior measure finite. I mean, a set could have exterior measure finite and be an unbounded set. So when I say it's a bounded set, I mean it's contained in a large ball, okay? Contained in a large ball. Let me continue here. Okay, so assume that you have an open set here, a closed set F, and you assume that it's a bounded set, so it's contained in a large ball. In particular, it's compact. Okay, so I'm actually going to assume that F is a compact set first. And in particular, you also get that the outer measure of the set, the exterior measure of the set F, is finite, okay? So let's assume first that we are working in this setting. Maybe it's helpful. Well, the exterior measure is finite because you can cover it with one big cube. All right. So now what do we do? Let's see. We can find an open set. Okay, so let's see. Given epsilon, we don't know. Okay, so I want to work with F complement, perhaps, right? Those sets are measurable. What do we do? No, that's okay. I'm going to use again, I'm going to try to use this proposition here. Okay? I'm going to try to use the proposition there. So, given epsilon bigger than 0, there exists an open set, so it's F, contained in an open set O, such that the exterior measure of O loses to the exterior measure of F plus epsilon. Okay? Because the exterior measure of any set is just the infimum of the exterior measures of open sets that contain that guy. All right. So now what do you do? Remember, we want to investigate O. We would like to have O minus F less than epsilon. But this is what we have now. The outer measure of O is less than the exterior measure of F plus epsilon. This thing does not imply this thing, okay? So if you try to use any sort of monotonicity, well, this measure of O minus F, if you try to use that O is equal to F union O minus F, and that these two sets somehow are disjoint, what you get is an inequality. Outer measure of O is less than or equal than the exterior measure of F plus the exterior measure of O minus F. So if you move this exterior measure of F to that side, you get that the exterior measure of O minus F is bigger or equal than, you get an inequality with the wrong sign. So the passage that you want to do is a little bit subtle. But anyway, let's try to do it. Okay, so you are with a closed set, compact, you construct, you gave me an epsilon, so there is an open set that contains, such that the exterior measure of this open set is just a little bit bigger than the exterior measure of this F, meaning by epsilon. Now what you do is you take this difference, O minus F. Well, O minus F is just O intersection F complement. So it's an open set intersection another open set. So therefore, this is an open set. Okay? And we have seen that for every open set, we can cover it by a disjoint union of cubes. So let me write this open set, O minus F, as a disjoint union of cubes Qj. An almost disjoint union. Okay? So this is what we did. I have my set F. I constructed a set O here, and I am covering this with some cubes. Okay? That's okay. So I'm writing O minus F as an almost disjoint union of cubes. Okay? Remember, cubes are closed for me. So I'm going to truncate this thing. Okay, so let's look at a certain set K, which is the union of Qj, say j from 1 to n. Let's put Kn here. Let's look at the first union of these cubes. So this Qn is closed, okay? And it's contained, Qn is contained in O minus F. So this means that, well, the Qn is actually closed and it's actually a compact set, right? Because it's bounded. The cubes are bounded. And it's contained in O minus F. So this means that the Qn intersection F is empty. So you have a compact set, Kn, disjoint of another compact set, F. So if you have two compact sets which are disjoint, they have a positive distance. Okay? This means that the distance between F and this Kn is positive. Okay? So prove this fact. If you have two compact sets which are disjoint, then their distance must be positive. Okay? If you have two closed sets which are disjoint, their distance doesn't have to be positive. You could have distance 0. If you just take sets of points that get very close, they are still disjoint, but get very close as you go to infinity. But if your sets are trapped, they are compact, if we assume that the distance goes to 0, you could have sequences of points in both sets that would get very close, very close, very close, but then this sequence would have subsequences that converge to a point. Since this point is compact, the point would have to belong to both sets. This is how you prove it, okay? But think about it. Okay, so now you have two sets which are at a positive distance, one from the other. Therefore, well, you can use what we have proved, right? We have proved that the outer measure of F union Kn. So now let's see. Let's see what we wanted to prove. Okay, so let's say F union Kn is just the sum of the exterior measure of F plus Kn. And we have seen that if a set is the union of disjoint cubes, I can just, the exterior measure is just the addition of the volumes of these cubes. All right, what else do you know? This F union Kn is, let's say, what do I want? It's contained in O, right? It is contained in O. So I can say for sure that outer measure of O is bigger or equal than this, because F union a finite collection of these cubes is certainly still contained in O. So the exterior measure of O is bigger or equal than this, which is adds up because they have positive distance. And this is since Kn is just a finite union of almost disjoint cubes, the exterior measure of Kn is just the sum of the volumes of the cubes. But now you have found a great inequality here. So this actually implies that if you move the exterior measure of F to the other side, you get that the sum of the volumes of these cubes, j from 1 to n, loses to the exterior measure of O minus the exterior measure of F. And this was the thing that in the beginning was less than epsilon. I just moved this exterior measure of F here. So this is less than epsilon. Aha. Okay. Since this holds for any natural number big N, here now is the point to send n to infinity. All right. Now what we do? Now we send n to infinity to get that the sum of the volumes of these cubes, the sums of the volumes of these cubes from 1 to infinity is less than or equal than the exterior measure of O minus the exterior measure of F, which was less than or equal than epsilon. But remember that our O minus F was just we wrote this open set as an almost disjoint union of cubes. And we have already proved that if a set, any set, is the almost disjoint unions of cubes, then the outer measure adds up. Okay, so the sums of the volumes of the cubes is just the outer measure of O minus F. So this is by proposition 1, 5. Okay. And voila, this is what you wanted, right? Exterior measure of O minus F is less than epsilon. Hence, F is measurable. Okay, so we are almost there. We proved that the closed set is measurable under the additional assumption that it was bounded, right? So we asked that closed set to be bounded. In the general case, what you do, the general case of f possibly unbounded, what you do is you let, say, bk be the closed ball of radius k centered at the origin, and you write your genetic set f as the union of f intersection bk, okay, from 1 to infinity. So this is, if bk is the closed ball of radius k centered at the origin, f is a closed set, intersection another closed set is closed. Therefore, this is a closed set, but now it's bounded. Since it's a closed and bounded set, we have proved that it's measurable. And then we invoke part number 3, that we have already shown that the countable union of measurable things is measurable. Okay? So we use this and use part 3. Okay, so we have now achieved, we have proved that closed sets are measurable. Once we have proved this, this is something we put in the pocket and we can use it from now on. Okay? Again, all of these things we proved from a basic definition. Once we prove these things, they become tools for us. So we are left with the final one. Complement of a measurable set is measurable. Let's do what we want. It is the final one. Part 5. I want to show that it's closed under complements. Okay, so let E be measurable. Let E be a measurable set. How do I argue? Okay, so what we can do is, let's say this is my set E. How do we want to argue this? Let's try this. Let's try this. Measurable. Let's try taking an open set. Okay, let's try to use the definition here. Okay, so then, given epsilon, so let's use it in the following. Let E be a measurable set, then for each n natural number, we can find a set ON open, such that the exterior measure of ON minus E is less than or equal than 1 over n. This is by definition of measurability, okay? Taking epsilon to be 1 over n. Okay? So I do, for each of these guys, a little bit of an open set here. Call it ON. All right. So now, what happens is that ON complement, since ON is open, ON complement is closed. All right? That's good. Since it's closed, by part 4, this is measurable. Okay? And where does, so if ON contains, so you go here, if this ON, if E is contained in this ON, this means that E complement contains ON complement. So you have a bunch of closed sets. Since ON is outside E, if you take E complement, will contain ON complement. And you're going to take, let S be the union of these ON complements from 1 to infinity. A bunch of closed sets. We have already proved that closed sets are measurable. We have already proved that countable union of measurable things is measurable. So this set S is measurable. Right? And this set S is, note, okay? So if each ON complement is contained in E complement, this E complement, which is fixed, also contains the union of these guys. This is what we call S, right? This S is contained in E complement. Now note that, let's take a look at the set E complement minus S. Okay, so this S is the union of all of these guys. So you can imagine what's going on, okay? So this is E, E complement is outside, ON complement is going to be inside, and as I send n to infinity, this ON complements will be trying to increase towards this E complement, okay? So I expect this set to be very small. But let's see. In fact, this is actually E complement minus S is E complement intersection S complement. And this is E complement intersection. What is S? S is the union of this ON complement. And this is E complement intersection. Well, a complement of the union of things is just the intersection of the ONs. And then what you have is that, well, E complement, this set, intersection, a bunch of intersections is certainly contained, this is certainly contained in this set, intersection, one of the guys, ON, for each n. Okay, for each n. But now I placed this set inside this one for each n. So what I get is that the outer measure by the monotonicity of E complement minus S is less than or equal than the exterior measure of well, maybe I need one more step here. E complement intersection ON is just ON minus E. So this loses to ON minus E, which was something that in the very beginning we assumed that this was less than 1 over n. And this holds for all n natural. Since the measure of this fixed set loses to 1 over n for all n natural, the only conclusion that you can get is that the exterior measure of this set is 0. Since the exterior measure of this set is 0, we have already proved part 2. You see here the importance of proving some of these things before. We have already seen that this set is then measurable. But then you write your E complement as E complement minus S union S. So you have just written your set E complement as a union of a set that is measurable, as you just verified, union S. And S was also measurable. You see, we have used almost all the first 4 properties to prove this number 5. So union of 2 measurable things is, of course, measurable. And there you have it. Your E complement is a measurable set. Okay? So what we have just proved is that, remark, in particular, the Lebesgue measurable sets they form a sigma algebra, okay? Lebesgue measurable sets form a sigma algebra. This is a consequence of we already proved. Consequence of 3 and 5. All right? So we get one more thing into our story now. So now we have the exterior measure, we have defined the Lebesgue measurable sets, and we have proved that this collection of sets form a sigma algebra. This collection is closed under countable unions and complements. And we have already seen that a sigma algebra, if it's closed under countable unions, then it's also closed under countable intersection, subtraction. You can do all sorts of set theoretical things. You can take in unions, intersections, and complements, okay? All right, so this is the collection that we want to work on. And we now prove the final ingredient for our theory here of the Lebesgue measure. So, part 3 of today, the Lebesgue measure. We have already seen that in this sigma algebra of Lebesgue measurable sets, we have defined the Lebesgue measure in a set in this collection as just the exterior measure of this guy. So now let's prove that this is in fact a measure in this sigma algebra. So proposition 3 of today is that if E is the union of EJs, okay, from 1 to infinity, disjoint union of measurable sets, then, well, we have already seen that the union of measurable sets is measurable, so all of them are measurable. So if you have a disjoint union of measurable sets, then the measure adds up. Measure adds up. Ooh. What should we do? All right. Let's see if we can get this. So I'll prove one inequality, and you guys will prove the other one, okay? Since you have a set, which is a union of lots of other sets, by the monotonicity of the exterior measure, we already have that this is less than or equal than the sum of the exterior measures of all of these guys, okay? Because, you know, M and M star are the same. This is the easy one. We already have it by just the monotonicity of the exterior measure. Okay, so what we have to prove? So now, this was mine. You guys proved the other one. How should I do it? How should we do it now? Okay, so we should prove the hard one, right? That the measure of E is actually bigger or equal than the sums of the measures of EJs. Oh. Okay, let's see. for finite. Good. Yes, I already have this for finite. For finite unions, yes. I have for finite union, well, be careful. No, we have for finite unions of cubes, right? We don't have for finite unions, we don't even have for two of these sets. We have for two, we have for finite unions provided that they are separated, remember? But this is not in place. So these sets are not cubes and they are not separated. So this is the real deal now. This is the crux of the matter. So let's see. So, okay, so let's make some assumptions first. So let us assume first that, let's say, all EJs are bounded, okay? Let's do what we did in the other exercise as we were proving. Let's assume that all of these guys are bounded. In the sense that's reasonable, because if one of these measures were infinity, since this guy is contained in this one, this other one would be infinity as well. And we would be okay. But I'm not only assuming that this measure is finite, let me also assume that the set is bounded. Okay. So now let's use the definition. I want to use the definition of measurability. Okay? I want to apply the definition to the set, not to the set EJ, but let me apply the definition to the set EJ complement. All right? So if we find, so this means that given epsilon bigger than 0, I can find a set such that EJ complement is contained in OJ complement, a certain set OJ complement, and the outer measure of, exterior measure of OJ complement minus EJ complement is less than, say, epsilon. Okay. Now, let me just call, since OJ complement is OJ, I'm sorry, this OJ. OJ is an open set. Let me call it OJ complement FJ. This is now closed, okay? OJ is an open set. Let me call OJ complement FJ. So what I want is actually, you could do, so I don't know if you can see this. Maybe I should go to the other board. What I'm trying to say is that if this is your set EJ, you can apply the definition to EJ and find an open set such that the exterior measure of the difference is small. But I want to apply I'm applying the definition to EJ complement. Okay? So I'm putting EJ complement inside an open set, which I'm calling OJ, with the outer measure small. OJ complement is that guy, so OJ complement would be somebody out of a certain set, and I'm calling this FJ. So I'm calling FJ to be OJ complement. So this is a closed set. Since EJ complement lies in OJ, then EJ contains this FJ. So you can somehow now revert the definition. Instead of considering an open set outside your EJ, you consider a closed set inside your EJ, such that the outer measure of your EJ minus FJ is less than epsilon. Okay, of course, you have to note the fact that OJ minus EJ complement is just OJ intersection EJ, which is just your FJ complement intersection EJ, which is just your EJ minus FJ, okay? So these two sets, the difference, you can see as EJ minus FJ, or you can see as OJ minus EJ complement. So, okay, so what we want to do is this. For any of those sets EJ, I want to find, and given epsilon, we can find a closed set Fj such that the exterior measure of EJ minus Fj is less than or equal than epsilon. All right, now what do we do? All of these guys are measurable. Let's see. Let me erase here, finally. What do we do? All right, so this is the inequality that I have to prove. I'm taking a closed set inside. Since I am assuming that my set EJ is bounded, the FJs are bounded. So the FJs are closed and bounded. They are compact. Now it's the moment to use the assumption that my sets EJs are disjoint. Because if they are disjoint, and I put inside each one a compact set, I will have disjoint compact sets. And then I will be able to add up, because they will have a positive distance. So this is why we do this. Inside each of these guys, EJ, and there you may have it on the other, touching EJ, you may have EJ plus 1. But since you put a little closed thing inside EJ, and you put a little closed thing here inside EJ plus 1, these two closed things here will have a positive distance. And then you will be able to add up. Okay, so this is the catch. Okay, so since EJs are disjoint, this implies that all the FJs that we have constructed here are also disjoint. Good? But now what? Now, so we can apply, so FJs being compact and disjoint from 1 to n will be separated in the sense that they'll have a positive distance from one another. So we can actually say that the measure of the union of FJs, J from 1 to n, will be the sum from 1 to n of the measure of FJs. Now let's see how we play this. We probably want, what do we want to do it? How do we want to do this? So let's try to do this. Let's go back here. And for each epsilon, let's do the 2 to the j trick again. For each j, we picked an open set such that this loses to epsilon to 2 to the j. So blah, 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 blah. This is less than 2 to the j. This is less epsilon over 2 to the j. Let's see if we have to do more. Now let's do a side computation here. Let's do a side computation here. You have that from the monotonicity, m of EJ plus m of, let's say, Fj plus m of EJ minus Fj. this is bigger or equal than of Ej. Okay, so I'm just using the monotonicity here. I'm writing Ej as Fj union Ej minus Fj. This is just the monotonicity. Now, there is a quantity that is bigger than this exterior measure, which is just the measure of Ej minus Fj, which is, so this thing here, there is something which is bigger than this guy, and this is just m of Fj plus this epsilon 2 to the j. So what you end up finding here is that this implies that if I move this guy to the other side, I will get that m of Ej minus m of Fj is less than or equal than epsilon 2 to the j. Okay? If I just move this guy right there. So you get this thing. Now let's continue. So what you want is to investigate the sum. We want to show that the measure of E was bigger or equal than the measure of the EJs. Of E. Yeah, okay. Okay, so this is what I want. All right. Okay. So this thing here, the union of Fj's, is contained in E, right? So then what you find is that M of E is certainly bigger or equal than the measure of this set. Because this set is contained in E. Right? This set is, each of the Fj's is contained in Ej, and Ej is contained in your
Let's go.
Okay. And we have already seen that we split this from 1 to n. Since this set is fixed, okay, maybe now it's the moment that we, well, yeah, okay. So then, okay, so this implies that M of E, I can actually move to infinity. It's bigger or equal than the sum from J1 to infinity of M of Fj's. Okay? Since M of E is bigger or equal than this for each n, I can send n to infinity. Okay, now I'm going to use this fact star here. That each M of Fj, so I'm going to use it in this form. Each M of Fj, if I move this to this side and this to this side, is bigger or equal than M of Ej minus epsilon over 2 to the j. If I use this right there, what I will get is the sum of M of Fj's is bigger or equal than the sum of J1 to infinity of M's of Ej's minus something that when I add up in J, I get, again, the powers of 2, and I get just minus epsilon. And that's it, right? M of E was bigger than or equal than the sum that we wanted minus epsilon. Since epsilon is any small number, since epsilon bigger than 0 is arbitrary, we conclude that M of E is bigger or equal than the sum of Ej's. All right. This was one way to do it. Maybe you can find a simpler way. These things that I'm doing are not necessarily unique, okay? Okay, good. So this was the inequality that we needed to prove, right? The hard one. So we have proved under the assumption that all the Ej's are bounded. Let's try to remove that. Let's try to remove that. Let's see. So in the general case, did we do? No, we might have done something. We might have done something slightly incorrect here, haven't we? I'm taking, oh no, yes, that's okay. I assume that these guys are disjoint. This is, remember, this is not now almost disjoint, okay? The EJs are really disjoint. That's part of the assumption. So these FJs are disjoint, and since they are compacts, they will be separated, right? That's okay. All right. So in the general case, what do we do? So now if you essentially, what you do is you can just, you use an essential argument when you want to cover your space, when your measure is sigma finite. Essentially, when you have to prove a statement like this, it's sufficient to prove when your sets are bounded, because when they are unbounded, you kind of intersect them with balls that cover the space. So what you do is that you take the balls bk, so let's say, so let again bk be the closed ball of radius k. Okay, so you take your balls and you start covering the space. And then you define, say, S for sphere, S1 like B1, S2 to be B2 minus B1, S3 to be B3 minus B2, and so on. So you start to define the rings, this one, this one, this one. So you essentially write your RD as the union, disjoint union of these SNs. Okay, so this is now a disjoint union. So what you do now is you have your collection E, which is the union of EJs, J's from 1 to infinity. You will intersect your EJs with each of these rings. Okay, so when you intersect your EJ with each of these rings, so if this is your EJ, there will be a part which is inside the inner ring. There will be another part inside the second ring. There will be another part inside the third ring, inside the fourth ring, and so on. So what you will do is you let your EJ to be the union of EJ intersection Sn, when n goes from 1 to infinity. Okay, so you let, so call these sets EJN, just EJ intersection with this Sn. Okay, so what you now have, what you have is that your original E, which was the union of EJs, is now the union of this EJNs over J and over N. Well, it's still a countable union. But now each of the EJNs is finite, is bounded, I'm sorry. Because you are intersecting it with a bounded set. Okay? So we have seen that the measure of E, from what we have seen, is the sum over J and N of the measures of each EJN. Because these are all bounded sets. And this union is disjoint. And now you have a sum of non-negative numbers, and you can choose to add them in whatever order you want. In particular, we can add first in N. So since each EJ is the union of EJ intersection Sn, and this is a disjoint union, of bounded sets, we can use the proposition that we proved again, the first part, to claim that this is just the measure of the set Ej. And this is what you wanted. The measure of E is equal to the sum in J of the measures of Ej. Okay, the same principle in general applies. Whenever you have a sigma finite measure, as in the case of the Lebesgue measure in RD, when you can cover your space by sets of finite measure, whenever you have to prove a statement, sometimes it's more useful, it's easier to prove when the sets involved are bounded. And then you prove for this case first, then you do the general case by just intersecting with these cubes or balls that expand your space. Okay? That's it. We have it, right? So we have constructed, so note, in fact, this is, in fact, the measure that we call little m is a measure on that sigma algebra. Okay? So we have constructed the Lebesgue measure. We have seen, so we have constructed a measure on the set that contains the Borel sigma algebra, because remember, it contains all the open sets were measurable. So it contains the Borel sigma algebra. It is equal to the volume of basic things, say cubes, and it's a complete measure. Okay? Open rectangles or open other things? Open, yes. We defined over closed rectangles, yes. Yes. Okay. Yes, I imagine it would be easy for some things and harder for others. You have to start from the beginning. So lots of questions emerge, okay? So, but we all agree that we have constructed this measure that we are going to call henceforth the Lebesgue measure, okay? Now, let's take a look at some of the points for discussion here. Okay, so there are several points. We started with answering Ruba's question. We started with closed cubes. Could we have started with open cubes? Yes. Could we have started with balls, closed balls or open balls? Yes, too. But this is not so, these things are not so subtle, not so simple to prove. You can try to prove this. Maybe with open cubes would be simpler, but with open and closed balls would require some thinking, okay? But the truth is, yes, you can start with some other basic objects that you know how to do the volume and start from there. Let's see some other properties, you know. A property that you guys should have in mind that I'm going just to write here, and we discussed the first items and I let the other ones maybe for you to prove as an exercise, is the following. You know, look, there's an interesting feature that this is the completion of the measure in the Borel sigma algebra. The completion in the sense that you have already seen. So let me call this proposition 4, and let me call this is the approximation of sets. Because at the end of the day, you want somehow to touch, to grasp these measurable sets. Who are they? Can I just give a set and you can tell me in an easy way how is this set? Is this set measurable or not? So the claim is, okay, so let E be a measurable set then this is of RD, okay? So we are all in RD from the very beginning. For every epsilon bigger than 0, you have the following properties. First one, there exists an open set O that contains your E such that the measure of O minus E is small. Second claim, there exists a closed set. So there exists a good open set from the outside. There exists a good closed set from the inside. So set F, that the set F inside E with the measure of E minus F less than epsilon. 3, if your set E has finite measure, there exists a compact set K inside E with measure of E minus K small. And 4, still in the setup, when the measure of E is finite, there exists, this is particularly interesting, a finite union of cubes, union of Qj. Let me write it. Finite union F, union of Qj, j from 1 to n, such that the measure of the symmetric difference, so we call it E minus F union F minus E, is small. Okay, so sometimes we denote by E triangle F this symmetric difference. It's just E minus F union F minus E. Okay, so this is just this union this sets. Okay. So 1 is essentially the definition. 1 is essentially the definition. Measure of O minus E less than epsilon. 1 is the definition, in fact. 2 is the definition applied to the complement. Okay? For every E, you can just look at E complement, find an open set, and then this is the complement of this is going to be your F. 3, you have to work a little bit. We work on epsilon because if the measure of the set is finite, it means that you can intersect with a big ball such that the measure of the remaining piece is less than epsilon. Remember, now since you have proved that's a measure, those basic properties that we proved for any measure, for example, if you have an increasing sequence of sets, the measure of the union is the limit of the measures of each set. So you can just take your set, intersect with balls. Since the measure is finite, if you get like a big ball of radius 1 million, the measure of this intersection, the measure of what's left is going to be very small. And then you take this intersection and apply the previous item to construct a compact, an F inside this thing. This is going to be your K. And the last one is that you have to prove that you can somehow work with the construction of, taking open sets. If the measure is finite, you can perhaps take an open set and cover it by cubes, and the measure adds up. Since the measures are finite, you can take your finite cover with n large enough such that whatever is not covered is small. So play a little bit with this. This is a very insightful exercise. The last one is particularly useful, for example, if you want to approximate simple functions. Remember, simple functions were linear combination of characteristic functions of sets. If you want to you can approximate this by step functions, which are linear combinations of characteristic functions of cubes. And then you pay a little price. Sometimes the price is very small. Okay? So this will come back in the discussion in the future. Sometimes we want to prove a certain statement for all integrable functions or for all LP functions. So it's sufficient to prove for a dense class of functions. So if we want to prove some statement, some linear statement for all the integrable functions, it's going to suffice to prove for simple functions, for linear combination of characteristic functions of sets. But then with statements like this, it suffices to prove for step functions, linear combinations of characteristic functions of cubes. Then if your problem is linear, if it adds up okay and if it multiplies okay, you can just essentially prove the property that you wanted to prove for just one cube, characteristic function of the unit cube, for example. This is a way some problems are reduced. A statement, a linear statement to prove for all the integrable function is reduced to prove just for one particular cube, characteristic function of one particular cube. But this is more, you know, I mean, this proposition says a little bit more. I am going to pass 10 minutes to finish this discussion today, okay? And next class we discuss something. So just as a corollary of this thing, as a corollary of this proposition 4, what you would get is let's see, so corollary 1. Perhaps I should say like this. So let E be a measurable set. So first one is that there exists a set which we call, let's call it G, which is the intersection of ON and from 1 to infinity ON open, such that G contains E, and the measure of G minus E is 0. Measure of G minus E is 0. This is just the first one. Here, if you take epsilon equals to 1 over n, if you take epsilon equals to 1 over n, and you baptize the open set from the outside as ON, so each ON contains E. If you take the intersection of these open sets, you still contain your E. So this G here contains your E. And the measure of G minus E, since this G minus E here is going to be contained in each ON minus E, so this will imply that the measure of G minus E loses to the measure of ON minus E, which loses to 1 over n. Okay? What's the moral here? This intersection, countable intersection of open sets, it's not necessarily open anymore. But if you just think about the Borel sigma algebra, so the Borel sigma algebra is the smallest sigma algebra that contains all the open sets. So if it's going to contain all the open sets, it will contain this G. Right? So this G is a guy in the Borel sigma algebra. What this proposition shows is that if I give you a Lebesgue measurable set, there is a Borel measurable set that contains it, such that the measure of the difference is 0. Okay? Second one, if we apply the same with 2, right? So there exists a set, and I don't know, call it D, union of the Fn's closed, such that D is contained in E, and the measure of E minus D is 0. This is good too, you know? And this is just follows from 2 by applying it with epsilon equals to 1 over n. You can take a closed, a countable union of closed sets. If you take a countable union of closed sets, this is not necessarily closed, but it's certainly a guy in the Borel sigma algebra. So what you're proving here is that for any Lebesgue measurable set E, there is a guy in the Borel sigma algebra D, such that D is contained in E, and the measure of the difference is 0. So you can really write, with these things, you can really write your E as D union E minus D. And there you have it. You know, I mean, this is a set of, you know, you're kind of adjoining the Borel set with a set of measure 0. Okay? With a subset of your E. So the sets essentially, let me see how I would phrase that way. Perhaps it's simpler if you just write it here, right? Your G, your your E is contained in G here. Your G here is your E. Is this what I wanted? Yes, right? E minus D. Subset of measure 0. Almost what I wanted, right? I don't know if it's this. Yeah. Yeah, this is what I wanted to kind of mention to you. So it's kind of a, in the sense, our Lebesgue measurable sets, they differ from sets in the Borel sigma algebra by sets of measure 0. And this is in the spirit of the exercise that I think I proposed to you a week ago, to say if you start with a measure on a sigma algebra, you can join the sets, the subsets of sets of measure 0 and create a new sigma algebra, and create a new measure, and this is going to be the completion. So in this sense, taking a look at these propositions, you can show that the Lebesgue measure is just the completion of the Borel measure, of the measure applied to the Borel sigma algebra. Okay. Let me stop here today. Maybe next class we start by studying a little bit of the invariances of the Lebesgue measure and showing that there are sets that are not measurable. The sigma algebra is not all the collection of subsets of RD. Okay? All right, let's stop here today.